Hello and welcome to the last video for 10.5 inverses of functions. So let's just remind ourselves, what exactly is the inverse of a function? Well, an inverse is, if you have a function and you invert it, you have switched x and y, right? A function in general, x is the inputs, y is the outputs. So if you have an inverse, you take the outputs from your first function, they become your inputs, and vice versa. Okay, your x's become your y's, y becomes your x's. Another unique aspect to inverses is that if you compose them together, what happens is they cancel each other out. All the operations cancel each other out, and you get just down to y equals x, or the function equals x. If you can do that for both of them, you can actually use that to prove that they are inverses. So if you compose two functions both ways, and you get x both times, then what you have are a set of inverses. Let's see if that's the case here with these two functions in example 1. Verify that the functions f of x and g of x are inverses of each other. So we need to compose these together, g of f of x and f of g of x, and hopefully what we get is an x as a leftover function. So we've got f plugging into g here, with the g coming first like that. So here's my g function, and I will plug in my x function to it. All right. What happens here, oh, I apologize, that's not quite the right way, because that 2 is not underneath. Sorry about that. It's on the outside. That minus 2 is on the outside. So what happens here? We see 1 over is going to flip this fraction back to a whole polynomial, x plus 2, and then we see those like terms, plus 2 minus 2 cancel. We get an x. Beautiful. All right. Let's go do the same thing for g of x. I'm sorry, f of g. We're going to put f inside of g this time. Here's f, 1 over plus 2, and then g is 1 over x minus 2. All right, we automatically see these two guys cancel each other out. Therefore, we get 1 over x. And again, we see that flip back. Again, we get x. So if we get x for both compositions, we have proven these are in fact inverses. Cool, not too bad. Some of these functions, though, some functions in general are not invertible. There is a certain unique aspect to these two that makes them inverses of each other. Notice how in both functions, if you plug something in, not only are you able to plug something into all of these, you don't get any answers, but what you get out of the answer will be unique each time. We have functions that sometimes you get the same answer. Still a function. Remember, to be a function, you just have to be able to get an answer, a singleton answer. If I plug in 2, I get 5. If I plug in 4, I get 3. You don't get, if I plug in 1, I get 2 or 6, right? That's not a function. So to be a function, you just need to get an answer. But to be a one-to-one function, what that means is that when you plug in something, you get a unique answer, okay? And they've expressed that algebraically here. Basically, if you get two of the same y, what you had was the same x, okay? So that's kind of the same thing, but in reverse. So for example, if I just had a table of functions, for two functions here, both of these will be functions. So unique x's, 1, 2, 3, 1, 2, 3. But then my y's were different. So functions, remember, you can have, as long as you have unique x's, you're good, right? And unique x's are good. If the first function had 2, 4, 6, but the second function had 2, 2, 6, the first function would be what we call one-to-one. Every x has a unique answer. 1 is the only answer that gives us 2. 2 is the only x that gives us 4. 3 is the only x that gives us 6. But in the other one, this is not a one-to-one function. 1 gives us 2, but 2 also gives us 2. So we have 2 different x's giving us the same y. That's not one-to-one. Now the name is quite literal. 1, 2, 1. 1x to 1y. And so For a function to be invertible, it has to be one-to-one, because what are we trying to do? We're trying to turn this function around. If we turn these tables around, we suddenly don't have a function in the second one. We have two y's going to the same x. You see what I mean? So let's take a look at these equations and determine if they are in fact a function. Okay, we're going to do this two different ways. The first way is just this idea of matching one-to-one. Well, we just saw that f of x is indeed a function because it's the same f of x from example 1 here. So this rational here, f of x, 1 over x plus 2. Let's consider the domain of this function. Well, if we choose -2, then we have a problem. There is a point in this domain that does not exist, right? But that doesn't make it not one-to-one. That just makes it a function that has a hole in the domain, right? It makes a restricted function, a restricted domain on this function. Doesn't mean we can't invert it. We just did. So let's kind of follow this definition. Let's pick a y. Pick a y. Pick an f of x. I don't know, 3. Why not? And let's see if there's any way any of these operations could give us two different x's. So we're basically kind of doing this in reverse. Instead of picking an x and seeing what we get, we're picking a y and seeing if we get two different x's. Solve this real fast. Move the 3 to the other side. So in this case, we get -2 plus 1/3 or -5/3. We get a singleton answer. Right now, it's not enough to just test the 1, but what we really want to look at is, are any of these operations ever going to give us two different answers? Let's see. Multiplying. Nope, multiplying gives you one answer. Dividing by 3, dividing by your y. Nope, that's going to give you one answer. Subtracting 2, no, that's going to give you one answer. And so this indeed will be invertible. Awesome. Now, there's another way we could look at this. Another way we could visually see if this was a one-to-one function. Remember, there's a visual way to see if something is a function. It's called the vertical line test, where if we look at the graph of this, which we didn't touch on a lot this year, but basically what happens is at left 2, you have sort of a baseball thread shape going on. This is give or take. So this is what this rational function kind of looks like. The vertical line test, if we were to draw a vertical line and then drag it across our function, we can see that this is not going to hit more than once. Now you might question right here, but that's just because I've drawn it super straight. Technically, it gets closer and closer to the asymptote, never actually hits it, and then goes across. So this is a function by the vertical line test. Well, there's a second test, you can guess it. It's the horizontal line test. The horizontal line test determines one-to-one. So it's the same idea. It doesn't prove that it's not a function. Basically, it proves is do you get the same y for two different x's? And in this case, we can also prove, no, we don't. We get one hit of this horizontal line to the function at all points. And so by the horizontal line test, we also see that it is a function. So it passes the horizontal line test. All right, let's do that again with this thing over here. This one, I'm just going to spoil it for you, is not a function. And we're going to talk about, or not invertible, pardon me. We're going to talk about y. It's still a function. G of x is x squared minus 2x plus 4. That is a function. There is no way that we can plug into x and get two different numbers. Things squared, you get one number. Things multiplication, you get one number. You add 4 to stuff, you get one number. So this doesn't even have a restricted domain. This is just a classic quadratic function. But let's kind of look at whether it's one-to-one. Is there a y that we plug in and we can get two different answers? I don't know, we did 3 last time. Let's pick 4 this time. So let's go ahead and pick y. And again, I'm not looking at 4 per se. I'm looking at if there's anything I ever see that might give me two answers. So, see, I got a quadratic here, which means I'm going to have to solve with factoring. Oh, that's convenient. Didn't even notice that. That was a happy coincidence. That just cancels that out all the way. Still got to factor out an x and then break it up. And here we see I'm getting two answers. There are two options that when I plug it into this function, I get the same 4. And that's a problem, okay? I can't plug in 0 and plug in 2, both get 4, and it be one-to-one. So if I try to turn it around, 4 goes to both 0 and 2, and that's an issue. So this is not invertible. Not invertible. Or it will not have an inverse. Now, again, we could prove this algebraically. We've graphed quadratics a lot. Let's see. I've got the points 0, 4, 2, 3, 4, and the points 2, 4, right? And then if I did a quick calculation, just a reminder, negative b over 2a would be 2 over 2 times 1, so 1, comma, plug in 1, you get 3. Okay, so our vertex, quick way to find a vertex, would be 1, comma 3, which would be right there, and that's our quadratic, right? So this is our actual quadratic. We could do it in the factored form. No, we can't because it doesn't have any factors. It doesn't hit the x-axis, so it's not going to help us to factor it. But we have our drawn parabola, which does pass the vertical line test, but definitely does not pass the horizontal line test. At almost every single point on this function, it hits twice on a horizontal line. The only exception would be the vertex or where it hits not at all. So definitely by 2 cases, not invertible. All right, we're going to talk a little bit more about functions being one-to-one and how to solve them in the next video. Just a couple other things to remind you of some inverses. Not only can we look at this aspect, proving if something is a function, but we can look at it as a reflection of the function. So if you recall from earlier chapters, the reflection over the line y equals x would also be an inverse. The line y equals x, what you get when you put two functions composed together, you get spit out that x, right? Over that line, you would see a reflection of 2 inverses, and you can go point by point. Excuse me. But basically, in general, inverses undo each other. All right, we'll see you in the next video for a reminder on how to find an inverse.